Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Welcome to another of the design patterns training. My name is Martin Schroeder at swedishembedded.com. If you have any questions regarding this training, you can always join our Discord server. You'll find the link at swedishembedded.com up in the corner. And if you have any other questions or you want to email me directly, you can email me at martin.schroeder@swedishembedded.com. In this module, we're going to talk about concurrency, and I've decided to describe concurrency or an introduction to concurrency as a design pattern because it is a pattern that we use when we want to control what the CPU will do next. So this is the main thing about concurrency, and there is multiple ways we can implement concurrency, but the basic idea is actually very simple. We're trying to decide what the CPU will do next. So let's get started. Let's go through this particular module here, look at the basics of concurrency, and then in subsequent modules, we're going to look at synchronization primitives and how we actually control what the CPU will do next. Here are three defining characteristics of concurrency pattern. Well, concurrency requires a scheduler. So we always need to have some kind of logic in our application that schedules the tasks, that manages priorities of the tasks, and that loads and saves CPU state. And this is what we do with software concurrency. If we need hardware concurrency, we need the same thing, but just in hardware. And we call that our interrupt controller, which basically does the same thing of storing and restoring registers, but does so in hardware in response to hardware events. But there must be some kind of scheduler or interrupt controller. Number two is hardware support. That's if we have we do need a basic hardware support in order to support concurrency at all, because we need to have a way of invoking the system interrupt that actually does the scheduling. So modern CPUs come with this support already built in, and there are actually special interrupts. For example, in the ARM architecture, we have the pend SV interrupt that are specifically designed for implementing concurrency. And number three, we need synchronization. If we use very simple interrupt concurrency, we need to disable interrupts when we're going to access data that is shared between the application and the interrupt. If we have more complex concurrency, we need more advanced forms of synchronization to avoid data corruption that is caused by accessing the same data from multiple places in our application. As we switch state, we need to make sure that we don't mess up the data. Let's look at some of the use cases of concurrency. And concurrency has some of very subtle use cases that really make concurrency an essential part of every embedded application. And number one is that concurrency helps us to save power, to implement system-wide power-saving modes. We can decide what power-saving mode our CPU will go into, and when there is no other work to be done, we can execute the wait for event instruction, for example, if we're using ARM, and the CPU will go into low power state until another event arrives. And concurrency is what provides us with a generic way of doing this, because we can basically do that in the idle thread to which we'll switch when there is no other work to be done. And point number two is that we get an ability to execute multiple hardware operations in parallel. And the reason this is hard without concurrency is because when we have multiple operations, even though the hardware is able to execute the operations in parallel, because the hardware itself is by definition parallel, so all peripherals are basically clocked with the same clock, if we simplify it, and all peripherals can most of the time do things pretty much in parallel. But we cannot make use of this to the fullest unless we have concurrency in place, because most operations that we do with our peripherals, they require, they're multi-step operations where we need to execute one thing, then wait for some I/O, then give another instruction, then wait for more I/O. And unless we have some kind of scheduler in place, what we have to do instead would be to loop on some flag and wait for an operation to complete. And we cannot jump into another place of our application and load another hardware register of another peripheral, which can run in parallel. And by doing so, we're basically stuck doing one sequence first, and then we need to do the other sequence. And with concurrency, we can manage both sequences in parallel. So we get the true hardware concurrency as well. And we can use the hardware to the fullest. Point number 3 is when we have multiple CPUs. So when there is, with multiple CPUs, we can balance the work that needs to be done, and we can achieve more. Basically, it's the same thing as with the peripherals. We can move each of the CPUs anywhere in our application depending on what needs to be done next. So because concurrency gives us the means by which we can decide what the CPU is going to do next, we can control more than one CPU in very efficient ways. And the last point is meeting real-time constraints. So if we need to respond to some event very quickly, concurrency helps us do that, because we can respond to, let's say an interrupt arrives and unblocks a semaphore. With concurrency, we can switch to another piece of code that is currently waiting for that event and execute that piece of code first before going back to what we were doing before. And without concurrency, we don't have that, because we have to execute to completion. So anything that requires us to execute to completion without the ability to switch context to another higher priority task prevents us from meeting our hard real-time constraints. So with concurrency, we can create truly responsive embedded applications. Some of the benefits of concurrency: lower power consumption, separation of tasks into time domains. And this is central. Actually, if you look at concurrency, the primary thing you're trying to do is you're trying to separate multiple sequences into isolated blocks of code so that you can execute a sequence in a sequential manner, but at the same time, you can do other things while this code is waiting for some event to happen. Then we have a basis for other patterns. So concurrency provides us with the groundwork that we need in order to implement other more complex patterns, such as, for example, async await. A lot of languages, such as Rust, provide the async await mechanism, but this mechanism itself needs concurrency in order to function. So for example, the async await uses a work queue to which we can defer work, and a work queue is essentially running in a separate thread, but it executes all of these events in sequence, giving the impression that we have asynchronous code. But in reality, we need concurrency in order to implement those things. And the last point is timeouts and repetitive tasks. So with concurrency, we can easily implement more complex timing mechanisms where we can, for example, schedule a work item and then submit it to the work queue. And to be sure that it actually also executes with highest priority, with essentially exactly when that timeout expires, without having to wait for completion of some other code. So we get very reliable software, and we get very reliable timing when we have the basic concurrency mechanisms in place. And some of the drawbacks, of course. Concurrency comes with increased complexity. It's more complex to manage concurrent applications because now we have to think about data access. Now we have to think about what other code can potentially interrupt what we are doing right now and modify the same data that we are maybe modifying as well. And this complexity is best dealt with by applying the kind of design patterns that I'm describing in this course. In particular, the object pattern helps us a lot with organizing our code in such a way that it becomes easy to reason about it when we add concurrency into the picture. Number two is the memory consumption. So concurrency always comes with a memory overhead, and even though this memory overhead usually is quite small, it's still a memory overhead that comes in addition to all the other variables that you have in your software. So if we look at a very simple scheduler like the Zephyr RTOS, we can get away with about 15 kilobytes of flash for the most basic scheduler, but it's still, and also some data memory as well. But it's still additional overhead. So that's something to keep in mind. But if you have a CPU that has at least 128 kilobytes of memory, then you should definitely include some kind of RTOS at the bottom so that you get all the benefits of having concurrency at the base of your application. And number three, performance. If you implement concurrency incorrectly, you can easily run into performance bottlenecks where you would be switching context more than necessary. So when you try to use concurrency to solve problems, it really helps to consider concurrency from the perspective of separating tasks into different sequential, basically into different time domains. So some tasks have their own, like most tasks have their own kind of heartbeat, and they need to execute a number of operations in sequence, but there's multiple such tasks in an application, and so we can kind of execute both of them interchangeably in parallel, but each one of them would essentially execute in sequence. And it's important to kind of try to separate the code into independent tasks like that, so that you can minimize the amount of locking, the amount of signaling you do between tasks, so that no task is essentially blocked by any other task most of the time. So if you follow those rules, usually performance is not an issue, because you get so much benefit from concurrency compared to how long time it takes to switch context, for example. All right, we are at the implementation stage, and I'm not going to go into great detail about the actual implementation of a scheduler, but rather I will look at the implementation of the concept of concurrency. How does it work with interrupts? First of all, how do we organize interrupts? How do the interrupt priorities work? And then we're going to look at the software side of things, how the corresponding task switching can be done in software with its own set of priorities, and how those two interact together. So we'll look at the full picture of all of the priorities taken together. And it's important to understand those concepts, because when you understand how the priorities work and how things fit together, it becomes easier to structure your application later and to decide when you need to use what synchronization mechanism, and what actually happens when you use a synchronization mechanism. Where is the CPU going to go next? That is very important to understand. If you don't understand that, it's always going to be kind of not clear to you what happens. For example, when you release a semaphore, when you give a semaphore, what happens then? Where does the code goes next? And when you understand all of the priorities, you can visualize that in your mind when you're coding, and that gives you unique insight into the function of your application, so it's easier to write good code. All right, let's look at the priorities and how they relate to each other. So this is a complete picture of priorities. We have at the bottom here the highest priority, and at the top here the lowest priority. And at the highest priority we have non-maskable interrupts, which cannot be disabled. And this includes, for example, the reset interrupt. The reset interrupt is basically what happens when your CPU starts, and that's actually an interrupt handler. And the CPU is going to execute this interrupt handler, and then this interrupt handler in turn sets up all of the tasks and eventually executes main. Now, in an RTOS concept, you will be going into main, and then this is going to be actually a separate thread with its own stack that will actually then continue the init process and create other threads and set up the rest of the application. Next, above the non-maskable interrupt, so this is the highest priority, and the way that is easier to understand this is that whatever has the lower number is the highest priority, and it's basically, if you think of this number as a place in a queue, then the lower number basically means that the item is going to be taken out sooner, so that also corresponds to the higher priority. So lower number means higher priority. And so above the non-maskable interrupt, we have zero latency RQs. And when you have an RTOS that supports zero latency RQs, it will configure the base priority of the CPU to such a level that you cannot, like when you do interrupt disable instruction, you would not be disabling the zero latency RQs. So you'll be just disabling everything above that, but not the zero latency RQs. So zero latency RQs kind of, it's a concept that is basically based on the base priority, which controls which interrupts are going to be disabled when you disable interrupts. And so if you have an RTOS that supports zero latency RQs, basically what it means is that you will be able to respond to interrupts even though you have, let's say, you have executed interrupt disable instruction. For example, if you're holding a spin lock and you're doing some operations that require you to synchronize access to some data between your application and some of these other interrupts here, but you cannot, with zero latency RQs, they are really kind of specifically designed for very low latency tasks that they cannot share any data with the application, because you cannot synchronize any access to zero latency RQ. So if you need to execute something that is very, very automatic and needs to happen at a very high rate and always on time, then you can use zero latency RQs with these special considerations that you cannot really synchronize access to any data between those interrupts and your application. Then above that, we have our normal IRQ priorities. So we have the SVC interrupt, which is basically the higher priority, and then we move to lower priority IRQs, and then we have the lowest priority interrupt handler would be the pend SV handler, which handles the actual context switch. And it's interesting to note here that all of the higher priority interrupts can interrupt the lower priority interrupts. And of course, if there is a spin lock held, then you can obviously disable interrupts so that they don't interfere with the lower priority interrupts. But the interesting part here is that when an interrupt, for example, gives a signal, let's say we are giving a semaphore. Let's say we are unlocking a semaphore here. Then what this will do is that it will pend one of these interrupts here. So when the interrupt handler completes, we will then go into the scheduler, and the scheduler will then decide where we go next. So for example, in this case, we have a work queue item that needs to run first, and then after that, we'll go to the unblocked semaphore thread, which is lower priority than the work queue. So it executes after the work queue item is done. But let's say we don't have a work queue item here, then we have the ability to actually move to the lower and lower priority task, and we will actually end up in the code that needs to run when the semaphore is unblocked. So on this diagram, we basically go from the highest priority, and then we can trickle down into the lower priority tasks and until there is nothing else left to do. So when there is nothing else left to do, we can put the CPU to sleep, and the CPU can actually completely stop and wait for the next event to happen. So in this way, we can control exactly what's going on. And the work queue, for example, is a cooperative thread. So this thread is never going to be interrupted by any other threads, but it will be interrupted by interrupts. And then we can have another higher priority cooperative thread. And then we can have lower priority threads, which run only when there is no other higher priority work to be done. And with synchronization primitives, we can control how these threads, how the CPU jumps between different threads and what it will do next. So we will look at synchronization primitives in the next consequence sections of this course. And I'll explain to you exactly what happens when you, for example, unlock a semaphore. or when you lock and unlock a mutex, or when another higher priority thread tries to lock a mutex that is held by a lower priority thread. So all of those things matter. And when you can understand this priority diagram, it becomes much easier to understand how things relate to each other. So this is a very simplified architecture. So we can, and this is actually something that's very useful in order to understand how things work. We can simulate the architecture in Renode. And what we do in Renode when we try to set up a new architecture, for example, is we start by creating a CPU core, and we then create the interrupt controller. An interrupt controller is a piece of hardware that is basically resolving all of the interrupts and instructing the CPU basically what interrupt handler to execute. And then we can have external interrupts, and we can have GPIO ports that connect to external interrupts. And the external interrupts connect to the nested interrupt controller, and then the nested interrupt controller connects to the CPU. So this is how all of this works. And in this way, we can have many different interrupts, and the interrupt controller will resolve the correct interrupt vector that needs to run in response to an interrupt. And the CPU, the interrupt controller will then instruct the CPU to basically save registers, jump to the new interrupt handler, and then when the interrupt handler completes, the CPU will pop all the registers, restore the state, and go back to where it was before. So this is a very simplified picture, but this is actually how we can define the hardware in Renode. So this is a valid file that defines a piece of hardware, but we do it in the Renode simulator. If you're not familiar with the Renode simulator, I suggest you look up Renode simulator, because it's a very useful tool, especially when working with firmware and setting up testing, where you want to basically test your whole firmware in software on CI server. So the key concept here is CPU registers. We have a number of registers that the CPU works with, and any intermediate state that results from different instructions that the CPU is executing is modifying one of these registers. And the registers, and then basically data is loaded from memory into registers, then some operation happens, then the memory is updated with the new value, so the registers are copied to external memory, or to a peripheral, or somewhere else. But the current state of the CPU is represented by these registers. So when we do a context switch, for example, we are executing an interrupt handler, or we are switching to another thread, what we're actually doing is saving the current set of registers into a place where we can store them, and basically restoring the state where the CPU, where we want the CPU to go. So if we want to jump to another thread, we will restore the state of the CPU that it had when it was executing that thread. And the state also includes the program counter. So we have the program counter, we have the stack pointer, and we have all the information that we need in order to restore the state of the CPU. And so every time we switch a state, we're basically saving current state and then restoring some other state where we want the CPU to go. And with interrupt concurrency, this happens automatically. This happens in hardware. So the hardware supports this kind of thing just to make it simple for us to define the priorities of the interrupts and then let the hardware do the rest. So we can set priorities. We can have our interrupt priorities grouped from the lowest number to the higher number, which represents the lower priority. And our higher priority interrupts will basically be able to interrupt the lower priority interrupts. So once we have configured our priorities, we can then respond to interrupts in a nested way. So this is what the nested interrupt controller implements, this kind of thing. And we get kind of a concurrency where we are able to respond to higher priority tasks quickly, even if we are executing another interrupt, and then we can go back to executing the other interrupt and continue basically to execute another interrupt here. For example, if this interrupt, if the low priority interrupt is set to pending, so this green box here, that represents that the interrupt is pending. So we can basically respond to this interrupt only after the higher priority interrupts are completed. So this one is pending here, and it executes right away. And then we go back to our QA, and then we execute the next pending interrupt, which is of lower priority here. And then so one thing we can do also is we can pend another interrupt from software. So we can set pend SV to pending, and then this will trigger the context switch once all of the other interrupts have executed. So here you can see why it actually makes sense to have pend SV as lowest priority interrupt, is because it doesn't really make sense to do this context switch before we have executed all the higher priority tasks. So we end up here when it's time to go to another, basically to exit the interrupt context and go to a thread. And this code here decides which thread we're going to run next. So this is a very powerful concept that connects the hardware essentially to the rest of the software and to the higher kinds of multi-threading and all of the multitasking that is implemented entirely in software. So then we get the software concurrency. And this is everything above the interrupt levels. So when we exit from our pend SV interrupt, we end up in one of the threads. And basically, thread switching is pending that interrupt from software and providing it with more information that will basically give it enough knowledge to know which thread to run next. And we control the threads in exactly the same way as we control the interrupts with priorities. So we can have multiple thread priorities, we can have cooperative threads that always run to completion, and we can have other threads that can be preempted. So one of the things that an RTOS provides you with is a default system work queue. And this is a useful construct that we'll look into more detail later, where we can actually schedule work or offload work to the system work queue from an interrupt, and let the system work queue run that item instead of having the interrupt run that item. And that has the advantage of allowing this work to be interrupted by other interrupts. So when we get above interrupt preemption, we get this whole new realm of possibilities where we can implement software concurrency, where we can decide exactly what the CPU is going to do next. So for example, when we start with main, we initialize our application, then we go to sleep. And when main goes to sleep, let's say there is another thread that potentially can run, that is ready to run, but it's lower priority than main, or in this case, it's the same priority, so main gets to complete. And exactly how this happens, exactly, what rules are applied to scheduling, that depends, of course, obviously on the implementation of the scheduler. But now we're talking about real-time schedulers, such as an RTOS scheduler, such as the one that we have in Zephyr RTOS. So then we run this thread, and then this thread is interrupted by an interrupt handler. So we jump here, and then the interrupt handler runs. Maybe this interrupt handler schedules some work, or basically submits work to the system work queue. So now this work needs to run, but it will only run after the interrupt handler is completed, because interrupt handler is higher priority. Then the work queue item runs, then we return to where we were in the default priority thread. Then this thread, let's say, goes to sleep. Let's say it's waiting for a semaphore. So it goes to sleep, we execute the idle thread, and the idle thread is actually then executes the power saving mode and puts the CPU to sleep. So now the CPU is not doing anything. It's just sleeping, saving power. And then the next interrupt arrives. So the only way we can wake up here is by some interrupt executing. So this can potentially be a reschedule interrupt or some other event, depending on how you configure your scheduler. So then your CPU wakes up, executes this interrupt. Let's say this interrupt gives a semaphore to another low priority thread that has been sleeping, and then this low priority thread runs after the interrupt has completed. Then this thread goes to sleep, and we're back in the idle power saving mode. And this is how we can structure our application when we have concurrency in place. So we can always have this ability to respond to events very quickly and to jump between different places in our application, almost like we have full control, literally, of where we're going to jump next. We just need to use the synchronization primitives in order to tell the system what to do. And so that's why we have all of the synchronization primitives. And we're going to look at the synchronization primitives in subsequent modules of this training. All right, that's it for an introduction to concurrency. Now, what are the best practices when actually working with concurrency? Number one is that you want to do the separation of tasks according to time domains. So basically the sequences of events that you want to execute in sequence, but then you want to have multiple independent sequences. And one of the ways to identify those potential sequences for placing them into different threads is to think about, okay, so you have this access to concurrent hardware, but you want to be able to execute those two sequences in parallel. And so that would be your two different threads. And we're going to go into a little bit more detail later on exactly how to do this. But I think personally, time domain separation is very intuitive way of thinking about how to separate things into threads. Number two is that you use interrupts only for loading hardware registers. So you do the minimal work necessary in an interrupt, and you offload any complex tasks, especially tasks that may need to sleep. Let's say maybe you need to, in response to an interrupt, maybe you need to do some I2C operations, which is a more complex operation. So you offload that work to the work queue, which allows other interrupts to execute, meaning that your application still remains responsive. And number three, you utilize the system work queue as much as possible. The system work queue is your primary way to avoid creating extra threads unless absolutely necessary. The system work queue is kind of, it's actually managed by a separate thread, but what's special about the system work queue is that you can basically submit work to this queue, and the queue will execute the work in a sequential manner, but it will do so outside of the interrupt context. So you can push things there from anywhere in your application, and you can also push delayed items that will execute after a certain delay, which gives a very efficient way of implementing, for example, time delays without having an extra thread that needs to execute some kind of wait operation. So system work queue is really a powerful concept that is provided by the Zephyr RTOS, among other RTOSes as well. And it's something that you should be aware of and use as much as possible. Some of the common pitfalls of concurrency is trying to reinvent the scheduler. So there is so many projects that try to avoid using RTOS, first of all, which is a mistake in itself, and then try to re-implement the scheduling algorithms. And no matter how much work you put into it, it's very hard to create something that is better than what's already there, because this problem has been solved since the 1980s, and the implementations haven't really changed. So there is this generic concept of basically managing the CPU and managing where it will go next. And there has been a lot of research put into this. So there's a lot of code that's already been done, that's already been tested, that is provided to you as real-time operating systems. And there is really no reason not to use it. So the biggest pitfall here is if you try to implement all of this yourself, unless, of course, you're doing it for educational purposes. And number two is that you're trying to use the threads as levels of abstraction. So one example is that, for example, you have a lower level thread that reads from a UART, and then another higher level thread waiting for the lower level thread to read a line. So you're trying to use the lower level thread as an abstraction, sort of as a line abstraction that feeds lines to a higher level application, and that is wrong. So you want to try to avoid those things. You don't want to create threads unnecessarily. So try to read as much as possible in the main thread, in the caller thread, really. So you should be utilizing semaphores, you should be utilizing work queue items to structure the sequences of your application, to structure, any kind of timeouts or delays, so that you can avoid precisely this pitfall of creating too many threads. So you want to avoid proliferation of threads. Don't create too many threads unless absolutely necessary. Alternatives to the traditional real-time operating system concurrency would be interrupt-driven concurrency. This is still used, especially if you have very little resources available to you. You can use the interrupt approach. And number 2 is state machines. Now, state machines work best if you build them on top of the conventional concurrency, because that gives you the most freedom. You can still have the massive benefits of conventional concurrency, as well as the benefits of state machines, where you can actually prove that a state machine is correct. You can prove it mathematically. So state machines have this additional benefit of being verifiable. And one of the things to understand is that you can't really replace conventional concurrency with state machines, because state machines are always run to completion. And if you want to have any kind of ability to respond quickly to events, you do need to have conventional concurrency in place. But there is nothing stopping you from using both. So you can have conventional concurrency at the bottom, and then as part of one thread, you might execute a state machine, which you are able to then formally verify and create more stable software in that manner, but still retain the ability to respond to hardware events very quickly. So in this module, I've provided you with a brief introduction to concurrency. We have looked at priority levels. I've provided you with an understanding of priority levels and how they relate to each other. So hopefully you have a foundation for understanding the concepts that we're going to cover next. And that would be the synchronization mechanism that control where the CPU will go next. So we're going to look in more detail into spin locks, semaphores, mutexes, conditional variables, and things like that. But all of them build on this foundation of understanding priorities. So that was the main goal of this module. And I hope we have achieved that goal so we can move to more complex concepts next. But before we do that, let's check your understanding of this module. So what is the main reason that interrupt-based concurrency is not enough for having full flexibility when writing higher-level applications? What limitations does it have? How does software concurrency enable you to make the most of your CPU without requiring major changes to your code structure and software architecture? How would you typically structure your priorities for maximum flexibility? And what we mean by this question is, how would you structure, for example, what priority would your work queue have? What priority would your main thread have? What other priorities could you create to make sure that you don't switch context too often? And what happens to an interrupt handler if another lower priority interrupt handler is triggered? So when will a lower priority interrupt handler run if another higher priority interrupt handler is currently executing? So that's it for this module, and I hope you learned something. I'll see you in the next module.